Hi everyone, and welcome to the advanced track. The advanced track is held by Well-Typed, which has been one of the real pillars of the Haskell industry since, well, forever. And this is the third year we're doing the advanced track, and it's always been really cool. So I'm quite excited to see the content myself. And today we have Adam, one of the partners at Well-Typed, talking about optics. And also we have Andres, who will help moderating and answering questions and so on. And yeah, so if you have any questions, you can ask those in the optics channel in this course. And yeah, please take it away, Adam.
Thanks very much, Jasper. And I mean, I'd like to say thanks for all the work you do organising Zero Hack. That's fantastic, and Well-Typed are glad to be involved in it. Just a few words about Well-Typed itself before we really get started. We haven't quite been around since forever. It's actually since 2008 that Well-Typed was originally founded. As two people, we've now grown to a team of about 18 Haskell consultants, doing a mixture of training courses. This is a sort of condensed version of the kind of thing we'd sometimes deliver for companies or for individuals to join in. We do a lot of Haskell software development and consulting work, and we have a team of people working on maintaining GHC. If you think any of that is something that might be useful to you or your company, please do get in touch with us, info@welltyped.com. So let's say a little bit about what we're going to talk through today. I'm going to start off by introducing you to the optics library and the general concept of optics. I'm hoping this won't be too advanced, despite the title. This is intended to be accessible, and so if you're someone who's a wizard with optics and lenses already, this probably isn't for you. On the other hand, I think if you've heard about them but haven't really got grappled with them before, I'm hoping it will be helpful. We're going to talk about what optics are, how they can help with working with nested data, and some of the patterns that they can use just to make your Haskell code simpler. We'll talk a bit about records and how optics can help simplify code that works with records, and then try and step back a bit and think about how we design libraries in Haskell, and some thoughts on how we can design a library that's really usable. I'd also like to mention that tomorrow my colleagues Matthew Pickering and Ben Gamari are giving another advanced track workshop on understanding memory usage with event-log.html and GHC debug. Some really exciting new tools that have been developed in the last year or two. And I encourage you to have a look at that. Do look at Discord for the instructions on how to get started with that. You do need to do some setup. So find the build instructions in advance. For this talk, we don't really need much in the way of setup. It's mostly going to be talking, and I strongly encourage you to interrupt me with questions. There's the Hash Optics channel on Discord, which Andres will be monitoring, and will forward questions to me. There's also this GitHub repo, which has the materials, including the slides, a few exercises, which, depending on how time goes, hopefully we might have a bit of a break in the middle of the session. And if you like, you'll be able to play around with some exercises and try out optics in practice. And there's a few links to further reading and other resources as well on there. So without further ado, let's get started with introducing optics. I'm going to be talking about the optics family of packages. So this is work with Andrei Rybchak, Andres, who's on the call today, and Oleg Grenras primarily. But the concept of optics in Haskell goes back a long way, and in particular, Twan van Laarhoven, Russ O'Connor, and Edward Komet have done a huge amount of work in introducing optics into Haskell, and the optics package is making use of many of their ideas and following along, but doing its own thing in a slightly different way. So let's see what that looks like and jump straight into the definition of a lens. If you've heard anything about optics at all, you've probably come across the definition of the idea of a lens in some form. So what is it? We're going to see a lot of these sort of standard slides in this talk, and if you look at the optics library, you'll see this pattern comes through a lot. So I'm going to present the type formation rules, which say what type am I describing, and then present the interface of that type with some introduction forms that say this is how you construct elements of that type, some elimination forms that say this is how you use it, and then usually some other combinators or some laws that describe properties that we expect values of that type to have. So for lenses, the basic concept is we've got some big structure and we're looking at one specific point within one specific substructure within that. So think of a field of a record, for example. So you've got a big type which will denote S or T, and within that a smaller type A or B which somehow forms part of it. Okay, and that I think becomes a bit more concrete if you look at how we make a lens in the introduction form. So if you've got a function that turns an S into an A, so it extracts the value of type A stored within the structure of type S, and you've got a function for updating the value. So given an S and a new value B, return a T, then that's how you build a lens. And we'll come on to why S and T are different and why A and B are different in a moment. So dual to that introduction construct, there are two basic elimination forms for lenses. So there's a function which we call view that says given a lens, you can extract out of it the function that gets the value of type A from a structure of type S, and a set operation that given a lens you can get, and a value to put back in the structure, you can turn an S into a T. And I should have said earlier, please do ask questions in the chat, and it's hard for me to gauge what experience people will have had with lenses already, and so as soon as it starts becoming unfamiliar, please don't hesitate to interrupt and ask. And then I'm
no questions so far.
Okay. I'm not going to say too much about the laws, just to make the point that they describe how we would expect one of these structures to behave in a way that makes sense. So violating them is typically not going to make your programs crash, but it might make your programs behave in a way that you didn't expect, and that if you want sort of to be able to reason about what your program is doing, then ultimately you're going to need to ensure that these laws are being respected, or the library that you're using obeys them. So essentially it says that if you have a structure in which you set part of it to a particular value B, and then view the same substructure, you should get the value B back that you set. Similarly, if you view the substructure and then just put that value back straight away, you should not change anything. And if you set twice, you should just get the result of the second call to set. So hopefully that's not too surprising. Let's have a look at an example of what this actually might look like. I mean, a very simple lens you might have is accessing the first component of a pair. I've deliberately named this differently to the optics and lens version because that's more polymorphic, whereas here we're just defining it for pairs only. So this says that if you construct a lens that uses first projection as the way to get a value out of a pair of A and an X, and to set a value back, you just take the pair and ignore the first component and insert the value of the second component. And then what can we do with that? Well, at first we can view using that lens and If we view the first component of the pair AB, we'll get A, and if we set the first component to C in the pair AB, we'll get CB. So hopefully, so far, so straightforward. One point that might not be quite so straightforward is the fact that we've got these two types, S and T, and these two types, A and B. So what's going on there? And fundamentally, what's happening is by changing the type of the substructure, you might change the type of the surrounding structure. So if you start with a pair of a Boolean, if you start with a pair of two characters, here, A and B, then there's nothing to stop you from setting the first component to be a Boolean instead. And then that will give you a term of type, a pair of a Boolean and a character. So that's why we have these multiple parameters. And so you'll quite frequently throughout lens and object libraries see this sort of 4-parameter pattern STAB. So you can think of S and T as being the outer structure, S being sort of what you start with, and T being the result of updating it. And then A is the inner structure contained within S, and B is the inner structure contained within T. Such that if you replace an A if you replace the substructure of type A with something of type B, then you'll change the outer type from S to T. And let's think about, so why do we care about this at all? So fundamentally, I mean, in itself, a lens isn't terribly exciting, but it becomes useful because it generalizes. So we'll see through the rest of this workshop lots of different optics, and together they give a really rich vocabulary for manipulating, accessing data. Central to that is composition. So if we have a lens that has S and T as the outer structure and U and V as the inner structures, and then if we have another lens that turns that from that U and V focuses on some even more specific substructure A, B, then we can produce a lens from the original outer structures S and T to the inner structures A and B. And so if you compose this first lens we've seen already, then that will just say, well, if you've got a pair whose first component is a pair, then it will take you from the outer pair containing a pair to the inner value of the first component. And that compositionality, I think, is really central to why lenses are useful, because you can combine a getter and setter together, and then you can compose them and make much bigger and more complicated objects, which you can then use with the eliminators that we'll see. And the other reason I think that lenses are useful is that they're first-class values, meaning that you can pass them around as arguments. You can store them in data structures. So this, I think, is where Haskell's capabilities for abstraction really come into their own. That you can write code that just takes a lens as an argument, and so you can generalize over the sort of concept of some structure having some property. And I don't think we're going to see any concrete examples of this here, but it can be a very, very helpful technique. But so there's more out there than just lenses, and so let's talk a little bit about what other structures we might be interested in. And one way to do that is just to say, well, what if we've got something that isn't quite as powerful as a lens? There's probably the simplest object to think about in the optics package is a getter. So a getter SA just gives you a function from S to A. So that means that you've got some structure and you have a function that extracts a value from it. And of course, that's weaker than a full lens, because a full lens allows you to both get the value out and then put a new value back. Whereas here we're just extracting values.
There is a question that says, I don't know how to pronounce the name, unfortunately, Zins or something. Sorry. In newbie terms, how do lenses compare with generics?
How do lenses compare with generics? So I think, generally speaking, they're solving slightly different problems. So generics is really about sort of programming with the structure of types. I mean, Andres, you may have different opinions on this, but I would say that the point of generics is to be able to write down the definition of the type, and from that have various things given to you automatically. So generic code can take advantage of the structure of types to define things which would otherwise be tedious to write by hand. Whereas lenses, I think, are more about, objects in general, I think, are about ways of extracting and manipulating data. You might use generics to create lenses, and we might see a little bit of that later on. So I think they're sort of complementary techniques. I hope that goes some way to help with the question.
Yeah, the only thing I'm slightly worried about is that, like, I mean, generics is being used for different concepts and different languages, and since the question explicitly says in newbie terms, I'm not quite sure whether this even refers to, say, GHC generics, or whether this refers to Java generics, or so. That's I've been trying to clarify that on the channel, but
okay, yes, I'm assuming GHC
okay.
generic. But,
okay, yeah, no, GHC generics is intended, and then I think you've hopefully answered it. Yeah.
Okay, yes, we won't talk really about generics today, I think, other than that they're going on behind the scenes in order to make some of the things work. Okay, but if there are no more questions for now, then so we've seen this notion of lens, we've seen this notion of getter, which you might think of as a lens that you can only view or just a function. Then what about the other direction? What if you can only set something rather than only being able to view? And that leads to the notion of a setter. So a setter says if you've got some function from A to B, then you can turn it into a function from S to T. This operation is a little bit more general than just set, because with a lens you've got a way to get the value out, so you can get the value out and do something with it and put it back. Whereas with a setter, we need some way to say, well, what was the value before we started? So most often you'll see this arising with the over function, which, given a setter, takes a function from A to B into a function from S to T. And you might see some relationship here with functors, and that is something we may discuss later. What are the laws for a setter? Well, if you change the substructure with the identity function, then nothing should change. And if you change a structure twice using over SF followed composed with over SG, then that should be the same as changing the substructure once, just composing the functions.
There is another question, which I guess is a partial follow-up to the contrasting with generics, which is by Michael, and says, how do lenses compare with uniplate, biplate, and similar mechanisms of type-based nested access to data structures?
I think so. Fundamentally, lenses give a more explicit way to talk about structures and substructures. There are various techniques you can use to basically say, given a structure, I want to sort of automatically find substructures of some particular type or with some field name, or some other method for sort of inferring which pieces I'm interested in. So lenses, at least sort of the core of it, is very much a very explicit method for saying, I'm going to combine. I'm going to talk about this structure with these substructures, and then of course we've got the full power of Haskell to construct those lenses. So you might use uniplate-like techniques for constructing an optic that says, given a structure, find the substructures using those techniques, and that I think relates to generics as well. But you can use generics to create lenses. You can use biplate type techniques to create optics. So they're very much complementary techniques. And lenses and optics are sort of trying to give in a way, a unifying abstraction, I think, that allows you to compose things nicely.
If you're willing to stay within this placement realm a little bit longer, Michel has a follow-up where he's asking, I have seen a lot of Java Python programmers comparing lenses to accessors, and that is certainly true for getters or setters, but it seems like lens libraries contain much more. So can you say something about that?
Yeah, I mean, I think we're gonna go on. There's a reason that we're starting with getters and setters, because that's sort of the simplest example, right? It doesn't get much simpler, but it gets a lot more interesting, and so I think yes, it's definitely true that lenses sort of generalize accessors or properties of types in a kind of Java style, but they give you a lot more, and in particular they give you a lot more in a compositional framework. So if you're using accessors in Java, you can sort of access a particular property and you can update it. And indeed with lenses, you can get, with some syntactic tricks, you can get things that look quite similar for accessing and updating properties. But you can also do a lot more. We'll see a little bit of that going on. Okay. Let's see. So far we've seen getters and we've seen setters. So the ability to extract data from a structure and the ability to update a substructure within a structure. And then if you put them together, you get a lens. But how are we going to use these things together? So let's suppose that we've got a lens like first, as I showed you before, and I've got an operation like over that applies to setters. Well, how am I going to combine them, right? So I want to use over to say I'm going to change the first component of a pair. Well, I could write a function lens to setter that, given a lens, produces the corresponding setter, right? From the interfaces we've seen, that's perfect. That's definable, and then I could use that function whenever I wanted to convert a lens into a setter. But that's going to get a bit painful. Okay, every lens is a getter and a setter, but just having one or the other doesn't give you a lens. So we want some sort of subtyping, but we don't have subtyping in Haskell. And at the same time, we don't want to be doing lots of explicit conversions from one to the other. So in a way, the challenge is, well, how do we design a library in which you can work with these different objects, and you can compose them, and you can use them without requiring that we have all these explicit conversions between different sorts of objects. And so how can we make a call like over applied to first well typed, given that we haven't got subtyping? If you've seen the lens library, then you may have come across some of these interesting looking type abbreviations, for all F, functor F, fact arrow, 8FB, test FT. We'll maybe talk a little bit more about how they work later on, but for now, I
sorry for interrupting again. But before you go into the von Laarhoven representation too deep, we have a question about the setter. Can you go back to the setter? Yes, in particular about the types of sets. Why can you explain? Can you just explain that type again? In particular, what sort of the A to B arrow part at the very beginning is supposed to mean, and how that.
Yeah, sorry, I think I glossed over sets a little bit, because in practice, you're not usually building setters directly. You're usually starting with a lens or something else, and then using functions like over, which work on setters. So if you look at over and sets, you'll see that they're essentially opposite to each other, right?
I think the confusion. Sorry, I think the confusion here is in particular coming from the fact that it's called a setter, but there seems to be an input. Like the A seems to be an input. So
yes, okay. So so it's doing slightly more than just saying you can replace the value within the substructure. It's really saying that S is some structure which has got 0 or more substructures of type A, and that you can change the values stored there. Okay, so it's doing a little bit more than just the set operation that we saw for lenses, because you can get access to the values that are stored, but only in the point at which you're changing them. Okay, so it doesn't sort of somehow this interface doesn't say anything about there actually being any values or how many values there might be. It's just saying that any values of type A that should be stored there can be transformed using a function of type A arrow B. Does that help a little?
Yeah, so there is a remark whether modifier might actually be a better name than setter.
Possibly. Naming is always hard. So in the optics library, we very much took advantage of the fact that the existing Haskell lens library had established lots of terminology that we just went and copied for reasons of consistency and to avoid introducing too many terms for things. But indeed, it's perhaps slightly surprising that something that's called a setter can do a little bit more than just setting. It really does modification. So yes, I think modifier would be a reasonable name if we were to name all these things from scratch. But naming is always difficult, and in particular when there are so many abstractions flying around that depending on your intuitions, different things can be useful or difficult names. It's really what we're trying to do here, I think, is sort of learn the vocabulary that the lens and optics packages use, and then work with those.
Okay, thank you.
Okay, so we talked a little bit about subtyping and the lack of it in Haskell, and so let's see how the lens package and the Van Laarhoven representation of lenses works to deal with this subtyping problem. So I don't want to go into too much detail about this representation at the moment. If you haven't seen it before, don't be put off. But the thing to notice is that The representation of a lens is some for all f, some constraint, and then something of type A to FB to S to FT. And then the representation of a setter is for all f, some other constraint, and then A to FB to S to FT. And this takes advantage of the fact that while we don't have subtyping in Haskell, GHD does support subsumption, which basically means it can automatically insert constraints and universal quantifiers and match them up in such a way that you get a sort of restricted form of subtyping just for quantifiers and constraints. So because the types themselves match, and all the interesting action is happening in the context, that means that if I've got a lens, I can use it as a setter because the appropriate subsumption relationship holds. If I've got something that works for any functor, then in particular it works for any settable, because the way settable is defined behind the scenes is more specific than saying that f is a functor. It actually says f is a particular functor. On the other hand, if I have something that's settable, I can't use it as a lens precisely because it assumes too much. It assumes that f is settable. When to use it as a lens, I really need to know that the thing I have works for any functor. And this is really quite remarkable, actually. It's astonishing that it works, and it's astonishing that it works as well as it does. So all you need to define lens is a type synonym. It just uses concepts in the base package. And in fact, even the function composition operation just turns out to do the right thing for composing objects. And the fact that function composition is denoted dot in Haskell means that you can even sort of get some nice syntax that looks like OOP style property access, which surely couldn't have been predicted when the notation for function composition was selected. So this is kind of remarkable, I think, and magical, but it's also complex, and that maybe can make lens libraries feel a bit harder to access. Was there a question?
Yeah. Can you go back to the von Laarhoven representation? So I think if I understand the question correctly by Javran, it is, does it matter that f is on the right-hand side of the definition? So I think the question is, does it matter that the quantifier sort of is on the right rather than that you make f an additional parameter?
Yes, it does. And so why does it matter? Well, I mean, I haven't talked about how this representation works, and I'm not proposing to get too much into that at this stage. But crucially, it relies on the fact that in order to have a lens, you need to have something that works for all functors f. And as I say, maybe we'll talk a little bit later about precisely how it is that something of this type can represent a lens with its view and set operations. But if you were to put the f on the left-hand side of the type synonym and instead have sort of lens BL STABF equals, then you'd be saying, well, for this particular choice of f, then I know that then I have something of this type, and so that wouldn't be strong enough. If you took a lens as an argument, then the operations on lenses wouldn't be implementable with that representation, because in order to implement view, for example, the implementation needs to say, well, I'm going to take this lens and I'm going to use it at a particular functor in order to implement view. And so that's why it's crucial that you've got this for all on the right. And this is called a higher rank type if you haven't seen these before. as I say, I don't want to delve too much into it because I want to focus on what optics are in the abstract rather than particularly how the lens library does things.
Okay.
Okay, so as I was saying, this is kind of remarkable, and it generalizes in so many different ways. There are so many different constraints you can choose. There are, I mean, some slight generalizations to the particular structure of the type that you can make in order to get this whole menagerie of different types of optic for different purposes. And yet there are some problems with this representation. I think, firstly, it's blurring together the interface. It's blurring the distinction between the interface of optics and their implementation, and so it's too transparent. So it doesn't have an opaque abstraction boundary. And so you see that, for example, if you ask for inferred types. So if you ask GHCI what the type of this first is, well, it doesn't tell you that it's a lens. It tells you that functor f arrow a to fa to something, and that's not what you're thinking about as a programmer who's working with optics. You're not thinking in terms of or shouldn't need to always be thinking in terms of this representation, and that just gets worse if you start composing optics together. So if you compose the first lens with a getter like 2 applied to naught, then that gives you a getter because of this subsumption relationship that says that if you've got a lens and a getter composed together, you end up with a getter, but that's not what the types tell you in this representation. Instead, they tell you that for all f satisfying these constraints, you've got some complex type. And another problem with this is that it allows you to express things that shouldn't be possible. So suppose you've got something that can just set. I mean, in this case, I'm using sets applied to the map function. And you've got something that can just get a value, like 2 applied to naught. So you've got a setter and you've got a getter. You shouldn't be able to compose those together because it doesn't make sense. There's no optic that can both set and get at the same time, because you just the interfaces just don't match. But of course, in this representation, there's nothing to stop you doing that, and indeed you'll get a perfectly well-typed term with this inferred type. And it just says that, well, if you can produce a functor that's contravariant and settable, whatever that means, then you'll get a term of this type. And in fact, you can't have such a functor that's contravariant and settable because of their definitions, but that's not made explicit. And so ultimately, this leads to notoriously bad error messages and confusion if you try to actually work with these startup objects.
There is a question by MMH, and that is if you contrast the transparency of the von Laerhofen representation with the possibility to have opaque types for lenses. Is there a compile time, runtime performance impact of this decision one way or the other?
There shouldn't be in general. We're going to talk about how we might do things differently, and we're going to do that by introducing a new type. And the general rule with new types is that most of the time they shouldn't come with a runtime overhead. It's difficult to promise that they will never ever introduce a runtime overhead, but I think fundamentally it shouldn't normally make a difference. And in fact, in the optics library, we try quite hard to make sure that we're not introducing any overheads. The real issue, the performance issue that you might worry about with lenses is not so much whether these new types are getting in the way, but whether you've got something that's just sort of doing lots of passing around lots of unnecessary dictionaries and things at runtime that ultimately should get specialized away. So it's not so much the distinction between having a new type or not, but whether the types at which you're using the optics are sufficiently known. And in practice, that's not usually a problem. And we use inspection testing to make sure that we're not accidentally slowing things down.
That was all about runtime efficiency, though. Is there a compile time aspect to this?
Oh, sorry. Yes.
I mean, the question was about both. I mean, so but
okay. Yes. So on the compile time front, I think in principle, I mean, potentially there is a lot of duplicated work that GHC may have to end up doing when it type checks these compositions and has all this subsumption checking to do, which would go away with an abstract U-type based representation. I haven't done any real investigation into that. I think in practice, this isn't where you hit compile time performance issues either with lens or with optics. I mean, there are other things in the realm of generics or various other issues that can lead to bad compile time performance. But I don't think this choice of representation tends to make a big difference one way or the other.
Okay.
So fundamentally, what have we seen? That I mean, the problem with the representation we have is that it's lacking abstraction. So fundamentally, you have to expose the implementation of the object. You have to say that a lens is a type synonym with this complicated definition, and you have to do that for subsumption to work. And that means we don't get a distinction between interface and implementation. And that leads to the problems I was describing with type inference with error messages. And so the idea with optics really is to try and design a library that uses opaque abstractions so that it doesn't expose the implementation in the same way, and yet retains some version of these subtyping relationships, so that you can use an eliminated design for setters when you have a lens, for example, or you can compose together different kinds of optic in a way that works and gives good type inference and gives good error messages. So that's what we're trying to do. Let's look at how that works in optics in practice. So we're going to start off just by defining some empty data types. These are only going to exist at the type level, and these are just going to act as tags to say what kind of optic is it that we've got. So we'll start off with a few for getter, setter, and lens. Okay, so these are just data declarations that introduce a symbol at the type level. They don't have any constructors. They're not ever used at runtime. And then we'll introduce a new type, as I was alluding to earlier, that says, given a k parameter, the kind of optic you mean, and I'm using the kind signature to indicate that I mean it to be one of these tags we had earlier, and an X list, which I'm not proposing to talk about for the time being, to do with indexed optics, which are a slightly more advanced topic. Then, and the usual 4 STAB parameters that we've seen. Then, so that gives you a sort of single representation for optics whose definition can be elided. I don't need to, as the library author, I don't need to tell you what my implementation of this new type is, precisely because it's a new type and the constructor is unexported, and so so we've got a clear interface implementation distinction. And then a pattern that we'll see cropping up again and again is that if we write a prime after the name of an optic, then we just mean here's one that doesn't actually take advantage of that functionality we talked about to change types. So optic prime just is parameterized by K, I, S, and A, and uses S in place of S and T, and A in place of A and B.
There is a question by Ryan Scott. Are there only finitely many optic kinds, or could a user conceivably define their own optic kind?
That's a good question. So at this point, we haven't seen it yet, but we're going to see shortly a reason why the library requires the universe of optic kinds to be closed. That there are only finitely many, and they all have to be declared up front in the library. Not at this point, but as I say, we'll see shortly why that has to be the case. I think it would be interesting to think about designing a library in which that assumption wasn't baked in, and that optic kinds could somehow be added subsequently. I think it's difficult to do that and have all the sort of nice tricks we can play to get good error messages and good type inference. And you're not really adding these optic kinds very often. I mean, in practice, having a small fixed hierarchy is not really a problem, I think. I mean, you might argue that there should be some that we don't support in optics yet, but that one might like to add. But
the way that you are defining this here by saying type optic kind equals type, and then giving different data type definitions for the different optic kinds, rather than having one promoted data type, seems to indicate that you are interested in this being open somehow. I think that.
Yeah, so this could be a closed promoted data type rather than a bunch of separate data types. And fundamentally, I sort of toyed with how I should present this, and ultimately went with what is actually in the optics library to avoid confusion. But basically, the reason we don't is that we get nicer error messages if we use this representation. So GHC has this really annoying habit of putting these little ticks everywhere if you use promoted data types. And I don't want people to be confronted with these annoying little ticks and wondering what they mean and why they're there. So that's fundamentally the reason. I mean, you might argue that it would be a little more type safe if optic kind was actually a union of these constructors. But I mean, in practice, we're not really generally writing code that's sort of polymorphic in an optic kind, because we'll see that when we actually start using these things, it always ends up getting determined by the operations you use.
Yeah, I've become quite practiced as well at typing -w no unticked promoted constructors really quickly. So, but I mean, I guess that still doesn't help for error messages. So
I mean,
for not getting the warnings in source code. But
I mean, it's. I mean, maybe we should make more of an effort to persuade GXC to be less aggressive at encouraging the use of these ticks and showing them in error messages. Fundamentally, what we wanted to do is present a simple interface and avoid any anything that looks unfamiliar. So that's why we've chosen to go this route. And,
okay.
Then, okay, so how do we define the getter, setter, and lens types? Well, we just instantiate this new type that we've defined with the corresponding tags. So lens is still a type synonym, but rather than being a type synonym for all f, functor f, arrow, blah blah blah, it's a type synonym for optic. And it would be really nice if I could persuade GHC that it should always print lens rather than optic a lens, no X, and so on. But I think this is the best we can get at the moment, and still have both the sort of the polymorphism we need, and also readable messages. So getter, setter, and lens are still type synonyms, but they're type synonyms for a relatively simple structure that doesn't then get further expanded by GHC when it's printing error messages. Okay, so this is shown us sort of what the interface for optic itself is, and then we need some way of relating different optic kinds. So the library is going to define a class is that says this optic kind K is an optic kind L. So a lens is a setter, a lens is a getter, and so on, but not a getter is a lens. And so that lets it offer a function cast optic that says if the source optic is an instance of the destination optic, then we can explicitly cast from one to the other. And so then, how do we use this in practice? Well, so far cast optic has sort of replaced the lens to setter function we saw earlier, but we really don't want to be writing cast optic at every call side. Instead, we want to sort of implicitly make use of these sort of subtyping style relationships. And to do that, there's a standard pattern that we follow, which is just to change the types of the eliminators. So remember I said before that over takes a setter. That's a little bit too specific, and instead what we're going to do is say, well, over takes an optic and it constrains the parameter K to be something that can be used as a setter. Okay, and similarly, the view functions that so previously we've had view for getters and view for lenses, and so we write a single view function that just takes an optic and says, well, we'll have a constraint that says K had better be usable as a getter, and so those cast optic calls then don't need to clutter up user code, but can just go into the library. And it's only when you're sort of writing a general combinator that works with optics that you need to worry about them. In practice, anything that actually just uses the library is typically not needing to use them. Okay, so that gets us some way towards this kind of subtyping that allows us to just naturally use an eliminator that's defined for setters when we have a lens, or in general, one operation with something that is more powerful. But then the other key thing that the Van Laarhoven representation gives us that we need to mimic is composition, and so we need to be able to keep track of the optic kinds in such a way that if you compose together two lenses, you still get a lens, whereas if you compose together a lens with a getter, you end up with a getter. And as we saw earlier on with the composition of a setter and a getter, that doesn't really make sense because there's no unifying abstraction. We'd like a nice type error if we try and compose a setter with a getter. We don't want to get an inferred type that then down the line can't be satisfied. And I've slightly given away the issue here, which is that we're going to need to change our composition operator, so we can't have nice dots anymore. We have these percent signs showing up.
Yeah, since you're mentioning type errors anyway quite a bit, so there was a remark by Anka that in GHC 9 and later, it seems like derived types or I guess infer types seem to present string, in particular, prefer string as a representation over list of characters more often. And so there seems to be ongoing work on not removing type synonyms quite as often, and whether a similar feature could also be used to prevent lens getting expanded to optic A lens, no IX?
Yeah, so it is true that GHG takes the position that where possible it should try and avoid expanding type synonyms. It doesn't always do so consistently, and it's quite possible that GHG9 is slightly better in that regard. I don't know the details there.
Ryan says something about that change only happened because GHC has special knowledge about string in the internals of the compiler. So, but that being said, perhaps I mean that's a start. Perhaps it can be made a pragma or something. I don't know. I mean, I'm just speculating here that one says that one can teach the compiler the special knowledge that is needed also for other type synonyms by providing some extra info, perhaps. I don't know.
Yeah, I something I'd really like to see, and I don't know if this is likely to happen at any point, but I feel like it should be possible to mark type synonyms as somehow contractible, so that that GHC should actually make an effort to, if it sees the right-hand side, present it as the left-hand side instead. Because as the library designer, if I have this this lens type synonym, if optic A lens ever appears, I really want to see lens instead. And so it'd be quite nice if I could tell GHC that and say that that this type synonym, it should sort of make an active effort to try and go back.
Try to reintroduce it if it's ever been.
Exactly. Yeah, and I think you probably want to do that on a sort of, as a sort of pragma on particular type synonyms rather than just doing it everywhere. Because, but fundamentally, the approach of sort of trying not to expand type synonyms just isn't in general going to be enough. As we'll see with composition in a moment, when you compose two things together, you're going to have to talk about this, the K parameter, and so GHC is going to end up expanding the type synonym to know what the optic kinds are that it's composing, and so sort of refraining from expanding type synonyms isn't enough to keep them always, but perhaps we can have a mechanism that sort of reintroduce them.
There is also a rather general question that has already been given some answers on the channel itself, and I'm not sure whether you want to go into it at this point, but are there some fundamental differences between the lens and optics libraries? How to decide when to use one versus another? And I think primarily people have been pointing to the documentation on Hackage that has a little bit of a discussion on this already.
Yeah, this is covered in the optics documentation, and hopefully will become clearer as we sort of go through the talk. I mean, fundamentally, I think what the optics library is trying to do is mimic a large subset of the lens API, but in a way that gives better type inference and gives better error messages. And is slightly more selective, which is why I say a large subset rather than sort of everything, because we're perhaps slightly opinionated about which are the kind of more useful features and which are the less frequently useful features, and so we're trying to make something that's a bit more accessible. Yeah, there's more to it than that, and I think we'll come back to the question of actually what
I think it's when we've seen something that we should discuss again when we're further along and have discussed more of the internals.
Yeah. Because I think we were just coming to one point, which actually is arguably one of the features that certainly is glaringly obvious when you start looking at optics, which is that instead of dot for composition, we've got percent signs, which I think for some people makes it immediately a no-go. But so how does that actually work? So I mean, just essentially just the same as is. We'll have a class join kinds that says, well, if I'm trying to compose together a K and an L optic, I should get an M optic. And so if I'm composing a lens with a lens, I get a lens. If I'm composing a lens with a getter, I get a getter, and so on and so forth. And so we have quadratically many of these instances, but given that the hierarchy is small and fixed, that's not really a problem. And then we can write a composition operation percent that says, well, if I have an optic K and an optic L, then I get an optic M subject to this join kinds constraint. So we can't use the dot function composition operator for optic composition, and I would argue that that's actually a good thing. I've seen code that's really quite hard to read because it uses dot both as a function composition operator and as an optic composition operator in the same line. And actually, I think fundamentally they're different things. They might happen to be implemented in the same way if your representation supports that. But conceptually, composing together optics is just a different operation to composing together functions. And so maybe we should have a different notation for that. And what does that then look like if we actually use it? Well, we get better inferred types, because if I compose together a lens with a getter, it doesn't say getter, which I'd like, but it does say optic a getter, which is a bit more useful.
Independently of the sorry, Adam. Independently of the question of whether using dot is good or not, there's a question whether the direction of composition is the same as in the lens package. Like the sometimes people are saying in lens functions, function composition actually works the wrong way around. Does percent work in the same way as optics, or does it?
Yeah. So
in the same way as lens, or yeah.
Yes, it does. So we're starting. If you look, we're sort of starting with an ST structure and then going to UV and then going from UV to AB. So this matches what happens with lens. And I mean, partially that's motivated by we just want to be reasonably compatible, and we want to be able to change from one to the other without unnecessary friction. But it's just a decision we make essentially, and it's a decision that we can make because we're defining the operation ourselves rather than as if by magic the preludes function dot does it.
Right, since we've already given up the use of dot as an operator name, I guess you could just define your own variant of percent that works differently, I guess.
Yes, I mean that's probably true for dot as well, isn't it? You could have you could in principle define composition the other way around if you wanted to, but I think that it makes sense to do optic composition this way, sort of starting from the outermost structure and moving into the innermost structure. But I can see that there is some sense in which it feels backwards if you use function composition. But then my argument is they're just different operations, and that if we notate them differently and think about them differently, then I think we won't get confused.
There is another question by MMH that has, in the meantime, already been answered by Andre, but but perhaps you want to answer it as well. Could the join kind class be replaced with a closed type family?
Yes, I mean, in fact, it was originally a closed type family, and we changed it because we found that this gave nicer inferred types. So some of the design decisions here are basically motivated by making things look as simple and straightforward as possible for the user. Fundamentally, I mean, it's using a functional dependency, but a closed type family would end up working out in very similar. There are very obscure cases where closed type families can do things that functional dependencies can't, but in practice they're not really the sort of things that you'd want to do here, because we're not really expecting users to be kind of writing definitions themselves that are polymorphic over this constraint and are doing all sorts of strange things with it. It's really a mechanism for getting type inference to give good results, and so we're making decisions based on what gives the nicest inferred types.
Okay, thank you.
Yeah, and as I was saying, then the nice thing about this is that then not only can we see what's going on when we compose together two optics, but also we can, with a little bit of custom type error magic, give a nice error message when if you try and do the wrong thing. So if you compose a setter with a getter, then we can give you a message that explains that that's not possible, rather than successfully inferring a type that you then can't use. Okay, so let's step back a little bit and talk about sort of what we've seen so far. And I want to sort of introduce this idea of generalizing what optics are as notions of substructure. So a lens, the first one we've seen, just being a structure which has got a substructure that you can get a value of and put back a value of. And we've seen getter, where you can extract a single value but do nothing else. We've seen setter, where you can, where, as I've hinted, we don't necessarily know how many substructures there are, but just we can replace their values. But we might think about, well, what might happen if, rather than having a single substructure as we have with a lens, we might have multiple substructures, or those that don't occur at all, or indeed two structures that are actually identical. And so we're going to sort of see that there's a slightly more interesting hierarchy here of different kinds of object that all fit together in this pattern. So far we've seen lens, getter, and setter, and we're going to see a little. We're not going to see everything that's mentioned in this diagram, but we're going to see a little bit more of it, and you can explore the optics library to find out a bit more about what some of these other things do. Okay, now are there any questions before we go on to the next section?
There is a question. Sorry if it was already mentioned, but what is the purpose of IX list? What role do they play?
Yeah, sorry, I should have been explained a little bit more that I'm not going to talk too much about IX list. So one of the features that optics offers is something called indexed optics, which maybe I'll talk a little bit more about towards the end if we have time. Mostly I'm going to ignore those for the purposes of this talk. So IX list is always going to be no X for no indices. But roughly speaking, the idea is that indexed optics allow you to sort of tag these substructures that you're working with somehow, so that for a lens, rather than just having a substructure, you have a substructure plus the index associated with it. And so that gives you a few more useful operations, but I think we'll need to see a little bit more before we can sort of appreciate what some of those might be. So I'm not proposing to go into that in any detail just now.
Okay.
Okay, so let's talk about then how optics might help when we're working with nested data, because I think that's where they start to provide useful functionality for Haskell programmers in practice. And to do that, we're going to need to look a little bit at records. So here's a data type person and a data type pets, each of which have got a few fields. And let's imagine I want to write a function which, given a person, extracts the age of that person and the age of all their pets. So this getAges function, well, how would I do it in sort of conventional non-optics Haskell? Well, I'm going to call the selector function corresponding to the age record field for person, and then map the pet age selector function over the list of pets. So far, so good. What if I want to add 1 to all the ages contained within the person? Well, okay, so now I've got to do some kind of record update where I'm going to set the age to be the value that it was +1, and I'm going to set the pets to be the result of mapping a function over the previous value of the pets list. And that function is itself going to do a record update. And you can see that this is getting messy. It's not very nice to work with. And so how might optics help make things a bit cleaner and a bit more compositional? Well, first of all, we're going to need to define some lenses. So let's recall that if you want to construct a lens, we can do that using the lens introduction form. So this is just the lens that, given a person, extracts the name field. And you'll notice there's this common convention that the field names start with an underscore while the lens drops the underscore. There are different possible conventions there, and we'll come on to some ways in which we can change exactly the details of how we work with fields, but this will do for the time being. And so in practice, what we're going to usually do is use template Haskell to generate those functions for us, so that we don't have to write them all out by hand. But fundamentally, this call to the make lenses template Haskell function isn't doing anything terribly interesting. It's just defining a person name lens and a person age lens and so forth. And so now that means that we can, if we want to get the name of a person, we can use view as we defined it before with a person name lens. Okay, but so that lets us get the name or the age of the person, but what about this get ages function, which given a person should return a bunch of results? And lens isn't quite going to do it for us, because that abstraction lets us talk about person having a field, person pets, which is a list type. But then, of course, a list could have multiple elements. And so we need something that will let us talk about those multiple elements. And that comes in with the notion of a fold. And to a first approximation, a fold is just an optic that's able to extract a list of elements from a structure. Okay, so just as a getter would let us, given a structure, would give us a single element, a fold you can think of as, given a structure, extract a list of elements. And so again, actually, we're not usually going to be constructing these things directly. So there's a function called folding, which will, amongst other things, let us turn a function from S to list of A into a fold. But more often what we're going to be doing is using to list of, which is the elimination operation that says, if you give me a fold, then, and a structure of type S, then you can get out the list of elements it contains. And here again, you can see this is class that we introduced before to be able to say, well, I want this to work on lenses, because if I have a lens that extracts a single element, or if I have a getter that extracts a single element, then I should be able to use it as if it was a fold, because if it gives if we know it gives one statically, then we can think of it as giving a list that happens to always be of length 1. And so what can we do with those these folds? Well, there are lots of useful combinators in the library that allow you to construct them and use them. And I can't go through all the combinators in this talk, so I'll leave you to look at the Haddix of the optics package. But in particular, there's an operation folded that says if you have a list of A, then we can have a fold that just extracts the elements of that list. And the summing combinator allows you to, given two optics, just produce the list of things in the first structure and things in the second structure combined.
There is a question by Morrow, probably motivated by the fact that you said a fold essentially produces a list. A fold sounds more like an unfold, or does it not?
Again, okay, yes. I mean, again, naming is always tricky, and we're taking the easy path of just copying what someone else chose already. Yeah. So a fold. What is a fold? It's a fold SA gives you the ability to extract a list of A's from an S. So, I mean, it's.
I guess it does. Like, it does give you the ability to extract the list in the most general form, but also to run all sorts of folds on it, right? I mean, so,
yes. I mean, I'm simplifying things a bit here by saying it's a list. You can also. I mean, and in fact, it's actually slightly more general to run all sorts of folds and combine things, not just by saying, well, I'm going to take all the elements of the S and put them together in a list, but you might say, I'm going to do something more like fold map. So sort of replace each element with the value of a monoid that I'm just then going to append together.
I think, probably the naming correspondence here is mostly inspired by the foldable class, or the essence of the foldable class is essentially that it is a class of a data structure where you, in principle, could extract all the elements of the data structure as a list. But of course, because you can do that, you can also run all sorts of operations on and perhaps even more efficiently on a structure of that type that you could also run on a list, all sorts of folds. And I guess that is probably the origin of the naming here. But,
yeah. There's a deep relationship to foldable, which again we may come on to. But I mean, for the purpose of writing this get ages function that we were talking about, where we want to get the age of the person and the ages of their pets. Well, one way to do that is to say we're going to use the person age lens as a fold, which we can do because every lens gives rise to a fold, and then sum that together with the with another fold that gets the age of each pet. And how do we build that? Well, we use the person pet's lens and compose that with the folded operation that says if you have a list of A's, then it will fold over each A in turn, and then compose that again with a lens for getting the age of each pet. And notice that it's nice that we can sort of define this independently of how we're using it. So we can define this fold that extracts all the ages contained within a person, and that's independent of whether we then eliminate it using list of to just get that list out, or as we were saying, if you use some other eliminator that might, for example, let you apply some transformation and combine the values monoidally, or there are different things you can do that you can sort of abstract this general notion of extracting multiple substructures from a single structure, and then everything composes very nicely. Questions at this point?
There's another more general question. Is there a relationship between lenses and attribute grammars?
I'm going to confess to not really understanding attribute grammars well enough, and I'm going to ask Andres if what do you think about that question?
I already said it's an interesting question, but I mean, I do know what an attribute grammar is. That is interesting because I haven't really thought about it myself. I mean, certainly, I mean, okay, so an attribute grammar is essentially a form of grammar where you can additionally define attributes that essentially describe computations that structurally work over the abstract syntax tree, right? I mean, so classically you have inherited attributes that flow down, and you have synthesized attributes that flow up, and you have all sorts of interactions between them. And clearly, in the sense that like what we've been discussing in the beginning, that there is a relationship between, say, a certain relationship between approaches such as uniplate, biplate that do predominantly treat traversals and lenses that can, to a certain extent, facilitate these things as well. I certainly think there is a relation, but I don't think I immediately see that it goes much further than that. I would probably say, in my opinion, probably the stronger connection is between attribute grammars and tree traversals being defined by some form of generic programming approach than immediately like lenses or optics and attribute grammars. But perhaps there's more to discover here. It's a question I mean, that's why I said it's interesting. I haven't really thought about very much. So,
yeah, certainly at the level of kind of tree traversals, I mean, that's something we're just about to come on to is essentially generalizes to precisely tree traversals, and there are some exercises in the GitHub repo that allude to that connection. So presumably from there you can then perhaps think about how via tree traversals and attribute grammar sort of gives rise to a way of traversing a tree structure, which you could then think about as a traversal. But perhaps I should first say what a traversal is, unless were there any other questions?
It's always possible that I'm overlooking things in the chat because there is a lot of communication. So if you feel like I've overlooked any question that you have been asking, then feel free to just repeat it or point me to it. But at the moment, no, I don't think there are any.
Okay, so let's talk about traversals, because we've talked about folds as a way of destructuring. Given an S, get a bunch of A's out of it, either as a list or combined in some fold type way. But what if we want to be able to update? And so we want to be able to say not just that S contains a bunch of A's, but also that by replacing the A's with B's, I can change the type of S into T. And this is where the types become a little bit more interesting, because I think there is not really a very satisfying sort of first order data structure representation that I'm aware of traversals in the same way we have for folds and lenses and so forth. And so that's where these slightly more interesting types start creeping back in. You might recognize this pattern that we've had, we talked about from the Van Laarhoven representation. And so we're going to explore in a little bit more detail what that means and where it comes from. But the first thing the thing to observe, I think, is that I mean, the sort of most straightforward way of building a traversal is to use this Van Laarhoven representation that we'll talk about shortly, and that you can use them by using a traversal function to get back to that. But of course, because if you have a traversal, you have a fold. You can also use to list of. And if you have a lens, then you have a traversal, so you can use these operations with lenses. And let's just sort of see our simple get ages and ing ages examples. There's, just like we had folded, traversed is the name for a traversal that, given a list, will act on each of the elements of that list. And then a join takes two traversals and combines them together in a single traversal, just as summing did for folds. There's a slight side condition here that the two traversals should be disjoint, so that they shouldn't visit the same element twice, because that would be problematic for the traversal laws, which we're going to see in a moment. But this gives us a very nice way to generalize that definition of ages we had earlier, to say, well, not just can I extract all the ages contained within the person data structure, but I can update them as well. And so I can just say, well, if I adjoin the person age traversal, because I can use a lens as a traversal, to this composition that says, well, for every pet, I'm going to go over every element of the pet's list and get refer to its age. Then so that gives a traversal of person that visits each of the ages stored within it. And so then I can use that to define get ages again, because to list off works on a traversal. But because a traversal is also a setter, I can use over. And so this function that was really quite unpleasant to look at when we were using nested record update syntax suddenly becomes rather more straightforward, because not only can I use sort of these nice compositional objects, but I mean, well, because I can do that, I can also give names to them independently and reuse them, and so you get this much more compositional structure that's more pleasant to work with than Haskell's existing record update syntax. But I promised to say a little bit about this representation of traversals and where that comes from. And what was going on with applicative F, arrow, whatever. So I think it's helpful to sort of have a simple example of what it is to be a traversal. And in general, traversals will follow this sort of fairly standard pattern. So what's happening? We have some effectful operation K, which has to have type A to F of B, and we're lifting it to a structure, in this case a list, and we're going to do that by inserting calls to the applicative operators in a standard pattern. So when there are no substructures, like in the case of the empty list, then we just use pure, and to say that there are no effects. And when we've got a cons, there's an A stored in the first component, so we call K on it, and then combine that using the applicative operations with the result of traversing the rest of the list. So intuitively, what this is doing is saying, well, I'm going to take some effectful operation and just do it over all the substructures and combine all the results. And that's a very helpful notion in just independently of optics to be able to sort of capture this pattern of taking some effectful operation and using it everywhere within a structure. So helpful, in fact, that the traversable class in base sort of captures that. Then to take this representation and turn it into an object style traversal, we just need to define it and then call the traversal VL function. And yeah, as I mentioned, in base, there's a class traversable which sort of captures this abstraction and says that if you've got some structure T such that you can lift effectful operations to act on all the elements, then it can be an instance of traversable.
Yeah, there's a question by Oskutuk. Why would one prefer writing a fold with folded and summing in the given example rather than a traversal? Since a traversal is also a fold, I don't see how writing just a fold is useful. It looks like just writing a getter instead of a lens.
Yeah, so it's true that every traversal is a fold, and so in this case, we wouldn't write the fold; we would just write the traversal. But of course, folds are more general than traversals, and so one way in which that arises, I alluded to already, that the adjoin operation that says that you can sort of combine two traversals into a single traversal has a side condition that says, and they had better not both target the same part of the structure, because one of the laws of traversals, which we haven't yet seen, but we will, is precisely has as a consequence precisely that you visit each of the substructures exactly once. So there are things that are folds that aren't traversals, and that's why sometimes it can be helpful to define something to define something as a fold, because it couldn't be a traversal. So, and similarly with getters, if you've got something that's a lens, you would typically define it as a lens rather than defining it as a getter. But it's entirely possible that one might arise because you compose together two things, and as a result of which you only ended up with a getter, or only ended up with a fold. But hopefully that helps a little bit.
There is also a question by Javran. I'm wondering whether it's possible to only modify the first n elements using lens or optics.
I don't know if there is a predefined combinator that does that, but it should be definable at least. If there isn't one, I mean, so the place I would look is in the optics.traversal and optics.fold modules, but it should be definable if it isn't there already, because actually this sort of representation of traversals is quite powerful. The fact that it works for any applicative, you can sort of pick and choose which effects you want to have available as you're doing one of these traversals, and so in particular you can turn it into a fold or a setter by making appropriate choices of the effects you want. But you could use state to keep track of how many elements you've seen, and you could traverse something only looking at the first n elements and then stop looking, I think. So
yeah, just while you started giving your answer, Javran already suddenly started suggesting using state himself, I'm assuming. I don't know.
Yes, I think that would work, wouldn't it? That you could certainly call you could use traversal with the state monad, and and that would let you get at it. I think that would. I don't see any reason why that would not work in general, and that you couldn't create a general traversal combinator that only looked at the first n elements of the traversal. It may exist already. I don't remember. Okay, so let's have another look at an example of traversals. This time for pairs. So here I'm going to assume that both components of the pair have the same type. And so if I've got a pair AA and I've got some effectful operation that turns A's into B's, then I can, under the effects F, get a pair BB. And I do it just by applying the effects to both substructures and composing the results using the afflictive operations. And notice that this isn't what you get from the built-in traversable, because that only looks at the second component of the pair. So by using kind of optics, you can use optics as a language for talking about which particular substructures you mean in a way that is a bit more precise than things like traverse give you. If you're familiar with data.traversable, then it fits very nicely into the Lenser optics framework. But also we can do things that we can't quite give a traversable class instance for, but we can still define it as a traversal and can still make use of that. because we're being a bit more explicit about actually how we're traversing a structure. I think it's helpful to see an example of what it looks like in practice to use a traversal once you've got one, because so far we've sort of used them as setters or as folds, but traversal, this more general eliminator that we saw, allows us to say, well, if I've got some effectful operation, I'm going to apply it to all the substructures. So if I have the traversal of pairs that I defined before, and I have an effectful operation that prints out a string and then reads in a new string, then by calling traversal from that, I'm going to say, well, I'm going to do the effects for the first component of the pair, and so print out the first component, read in a new value for the first component, and then similarly for the second component. And this is a kind of trivial example, but this general pattern of defining a traversal that talks about which pieces of a structure you're interested in, and then independently calling that to do some effects at each of those structures is extremely general and extremely useful. I talked a little bit about well, I didn't talk very much about traversal laws, but I mentioned that they exist, and that I'm not going to go into the details of why these work. They generalize the setter laws a little bit and say that essentially a traversal takes a structure and visits some number of substructures. Crucially, it can't change how many substructures there are, and it can only visit each of them once. So that means that, for example, you can have a fold that extracts the elements of a set. So you can convert a set to a list easily enough, but you can't have a traversal, at least not a law-abiding traversal that acts on all the elements of a set, because if you change the elements, then you might end up changing their relative order, and so you're going to change the structure. And that again sort of alludes to why you might want to define a fold rather than just a traversal, because sometimes folds can do more things because they're less restricted by the laws. Now I think we should probably take a break shortly, but before we do that, I just want to then now draw the link back from this representation of traversals we've been talking about to lenses, and notice that the type of traversals we've seen is actually again very similar to the Van Laarhoven representation of lenses. It says if you've got some effectful way of transforming an A into a B, then that the traversal can change that into a effectful way of transforming S's into T's. And so a lens is exactly the same, except rather than saying, well, I'm allowed to combine the effects using applicative operations, instead I only have access to the functor operation, fmap. And so if you squint a little bit, you can sort of see, well, okay, then that means that if I've got access to the applicative operations, I can have pure, so I can have no substructures that do effects. And I can have star that says I can combine multiple results. And so somehow there's a relationship to the idea that you can have a traversal visiting multiple elements, whereas for a lens, because you've only got fmap, there must be precisely one substructure. You can do the effect once, and you can see that a lens can immediately give rise to a traversal in which it does its effect exactly once, and it has exactly one substructure.
There is a question that, I mean, basically, if you have something meaningful coming out of all this for functor and for applicative, then what happens if you put monad there?
Yeah, it sort of feels like you should get something more useful, doesn't it? And it turns out that you don't particularly, and I'm not sure I have a very good memory for why that doesn't lead to anything new that's interesting. So yeah, I can certainly say that it doesn't give rise to sort of new useful structures, but I forget exactly the reasons for why that's the case.
Okay.
So yeah, so what have we? I mean, we've seen so far. Going back to this diagram now, sort of looking more at traversal. Well, we've seen that a traversal, which you can use as both a fold and a setter, and you can produce one from a lens. Well, I think not go too much into too many of the other structures, but I think this would be a good point to stop and take a break. So I would encourage you to have a look at the GitHub repository, which we might be able to find the link for. There we go. Which has got, if you'd like to explore some of this more, there are some exercises you can try. And I'm happy to have a chat on the channel and answer specific questions. So we'll take a break for I think about should we say 20 minutes and sort of reconvene in 4 p.m. CEST, 3 p.m. BST.
Okay.
Are there any questions I should answer from the chat before we pause?
I think no, there was a little bit of a discussion, essentially just praising traversals as being extremely useful. In particular, also because I mean there are many types that can't easily be made an instance of the traversable class, but you can still define meaningful traversals over them, right? And that has triggered a bit of discussion, but I don't think there was anything that was directly a question. I'll scan a little bit, and perhaps we can pick this up after the break if there are any things that I have overlooked. Okay. So I guess yeah, we do like 17-minute break roughly. And then resume afterwards. Okay. Okay, so let's just get started again. I don't think there are any new questions right now, so I'll just hand over to Adam again to continue.
Okay. So we've talked a bit about kind of different types of optic. I want to take things in a slightly different direction now and talk a bit more about records and different mechanisms that exist for accessing records. And this is going to kind of go into territory of a few of the different extensions that are available now in GHC or that are coming up. So we've seen sort of part of the records problem in Haskell is that nested updates can be messy. Another part that I think was mentioned briefly earlier is this kind of limitation that every record field within a single module has to have a different field label. And so we had to have these person name and pet name fields previously. With the duplicate record fields extension, that limitation is removed, and we're allowed to have a name field for person and pet in the same module without a problem. We can't also define name as a top level function or binding in current versions of GHC, but in GHC 9.2, the no field selectors extension will make that possible. So what happens if we switch on duplicate record fields? Well, actually, a lot of the time, there's not really a problem with having potentially duplicated names, because much of Haskell's record syntax uses the data constructor name anyway. So if we have a record construction like this call to McPherson, we have these field names which might be duplicated, but that doesn't matter because the data constructor name tells us which field we mean. And similarly, if we pattern match on McPherson, there's no question as to which field we're using because the data type is there already. Record update gets a little bit more interesting. In this case, it's allowed because there's only one type that has age and the pets fields. But with selector functions, we're fine as long as there is a single data type that has a field of that name. So because only person has a pets field, this particular function is going to be accepted. But what about the name field? So if I write something like this, then there's a problem, right? Because do we mean name as a field of person or name as a field of pet? It's not obvious from the types. And while there is some functionality within the duplicate record fields extension to use some type information to figure out which type you meant, that is being removed and isn't really going to be a possibility because it was generally not popular. So what can we do instead? And I mean, I would be remiss to not point out one possibility, which is simply not choose clashing names. Right? We had some success previously with just using type-specific prefixes, and that works, and maybe that's the best option for your use case. I think inevitably, once you've got sort of different names to disambiguate, you run the risk that your code is going to be harder to understand, both by readers as well as computers. So that's a possibility. But let's explore some of the other possibilities for how we might refer to these record fields. And another, I mean, I should mention, sort of, if you like, non-clever typed possibility is to simply use the module system. And actually, this can work quite nicely if you use a qualified import to say, I'm just going to import the person type and its fields, qualified as person, then I can just use person as a prefix where I need to, and avoid any possible ambiguity. And that's nice because it just works in sort of Haskell 2010. There's no need for any extensions. There's no clever typing, but it gets to be verbose. And if you have lots of fields that have common names, then this can get a bit tiresome, especially if you have to do this in every module to introduce all these qualified imports, and you can't do it in the module in which you define a data type. So what else might we do to disambiguate if that's not enough? In GHC 9.2, there's going to be a new overloaded record dot extension, and that is going to introduce a new syntax for accessing fields, which you might find familiar if you've used more or less any language that isn't Haskell. That you'll be able to write a dot followed by the name of the field, and then the type class mechanism will be used to resolve which fields you mean. So, for example, if you're writing this function that I had previously to test if the person's name is Alice, well, then you can just write p.name. And how does that work? It's going to introduce a has field constraint that says, well, whatever the type of p is, it had better be a record type containing a name field with some type A of the field type, and then the compiler will automatically solve the that has field constraint. So it's a new extension. It's a new syntax. There's syntax here for access, which will be in GHC 9.2. There is a plan to implement updates as well. The syntax for updates will be in GHC 9.2, but the has field type class doesn't yet have support for doing updates. So actually using this for updates is going to need a bit longer. And this, I mean, it'll be interesting to see what kind of reception this gets when GHC 9.2 is released and this is more widely available, because it has a significant advantage of simplicity, but it doesn't have all the nice sort of compositional functionality that we've been talking about. And in particular, the example we had where you wanted to extract the ages of the person and all the pets. We needed something a little bit more than just a lens for a field. We also needed to be able to fold over or traverse the list. And so I think there's the record dot syntax isn't going to subsume what's available in the lens and optics packages. Instead, the mechanism that optics makes possible really is exploiting another feature of another GHC extension, overloaded labels. And if you haven't seen the overloaded labels extension, then what it does is gives you this new sort of syntactic form hash name, where it's a little bit like isString, the overloaded strings class, where you can have the value that you mean depend upon the type by which you're using it. But in the case of his label, the text of the label is also relevant. So if you write hash name, then that can have any type T, subject to his label constraint that depends upon the actual label you wrote. And what that in practice means in optics is that you can use hash name as an optic to refer to the fields as either, as a lens in the case of a simple record field. So I can use view hash name to get back the selector, but of course, because hash name is in this context a lens, I'm going to be able to use all the machinery we've seen already to build up more interesting structures. So it doesn't just give you selectors, but gives you lenses. And so that, and of course we haven't had to define anything in advance. Whereas with the approach we saw previously, you needed to use either template Haskell to define person name and pet name lenses corresponding to each of the fields, or you had to define them all manually. Because we're able to do this just using sort of this one new piece of syntax built into GHC, and then use generics behind the scenes to construct the object. Then there's no need to sort of predefine anything. You can just use these objects wherever you need them. A potential downside is that because this overlaid label syntax may be unfamiliar and may be used differently by different libraries, it may be a little bit more unfamiliar. But were there questions?
I have a question.
Go ahead.
Is there a similar concept for prisms or constructors?
Yes, I think I haven't really going to talk very much about prisms today, but I believe you can use. I think the syntax is hash underscore, and then the constructor name starting with an uppercase character. I think we have automatic support for that. I can't actually remember because it's relatively recent that we've sort of had built-in support for this in optics. The generic optics package, which is a version of generic lens adapted to use optics, has had the ability to construct these things for some time. But it's only relatively recently that we added them to optics. But I think there's support for prisms as well. But I mean, certainly in principle, you can have one of these labels. It doesn't have to just refer to a lens. It can refer to an optic of another kind, and so you could use it for a prism or a traversal if you have a field which occurs in some constructors but not in others.
Okay, thank you.
Let's have a look at what this looks like in practice. So as I mentioned, we're going to need to use generic deriving to be able to generate the optic behind the scenes at the moment. But then we can just write definitions like we had them before, but putting a hash sign in front of each of the field names, which tells GHC to use the overloaded labels mechanism, and then everything will get resolved for us. So there's no need to predefine the optics we're using. So what does I'm going to skip over that a little bit. I mean, looking a little bit more closely, how does that actually work? I mentioned this is label class. So that has a single method. This is just essentially a normal class defined in base, which has a single method from label, which says how the label should be interpreted for a particular symbol and at a particular type. And then when I write hash name, that gets desugared to a call to from label with the particular field name specified. And then in order to translate labels into optics, the objects library provides an instance for these label class that delegates to another class label object, and label object then is the thing that allows us to say, well, for a particular label whose name we know statically at the type level, we can determine what object kind it's going to be and what its type is going to be. Okay, and then what we can then do with this, I should warn that some of the syntax is potentially getting a little bit hairy here, but for those who prefer to use sort of operators rather than names, I've mostly been using names to date, but there are operator versions of view and to list of and the over function and so forth, which we can then use together with either overloaded labels or predefined lenses like template Haskell, as we saw earlier, in order to get something that looks sort of a bit more like OO style property access. So this caret dot operator is view, and it just means, well, get the name field of P. The nice thing being that that isn't just a field name, it's a lens which we could build up by composition. And so here get pet names uses a caret dot dot operator that is syntax for to list of, and so it's going to say, well, use this fold, which I'm defining here, that visits the name, that extracts the names of all the pets contained in the structure. So this, I mean, this is perhaps getting to the point that the syntax is just too complex and confusing, and maybe the hash signs are too much, and maybe we're better off going to a version that uses type prefixes instead, and predefines defines the optics. I think I don't want to sort of commit to one single approach as definitely the way we should work with field names and objects, but more say that there are choices here and different possibilities. And I think with some of the recent sort of GHC extensions, it's perhaps going to take a little bit of time to work out exactly what the preferred approach is. But there's a lot of possibilities developing.
There's a question about error messages in the context of overloaded labels. I mean, because you, I guess, have been placing emphasis on good error messages a lot before. I mean, how do they look the moment something goes wrong and you use overloaded labels?
Yes, okay. So I suppose it's true that you could end up in a situation where you're using an overloaded label at the wrong type, that you're not sort of requiring it to be an object because you're not using it in a context that expects an object. And in that case, I think you could, I mean, you'll end up with a message that talks about the isLabel class. So that as always, whenever you sort of introduce any more polymorphism, there's a risk that you'll fail to infer the relevant pieces and end up with something that gives rise to some more confusing errors. So yeah, so I think, I mean, error messages is one area where overloaded labels potentially make things a little bit more complex, but somehow that's to some extent going to arise if you want something that can use type information to disambiguate which field you mean. I mean, I suppose one issue is that the overloaded labels are not tied to records or objects in general. They can be used for other things, and so perhaps that means they're a bit more general than ideally we would like. I mean, the history here is somewhat complex, but the overloaded labels mechanism was originally introduced, kind of envisaging being used for lens and for the Van Laaren representation. But the difficulty with that is that we've got this is label class, and if you're using the Van Laaren representation, then what does the is label instance look like? That it needs to be an instance for the function space, and not just kind of any function, but functions that look like these lenses in Van Laaren representation, so A to FB to F to FT. And so I think there are packages out there that actually allow you to use overloaded labels to construct Van Laaren representation lenses. But because of that kind of lack of a wrapper, it's you need an orphan instance, and it gets a little bit messy. For optics, there's an advantage there.
Yeah, so there was a there was another question related to this. I mean, I guess it's just sort of a clarification. Is a label always a lens or always an optic?
It doesn't have to be. I mean, as far as this label is concerned, it's just a anything that you can get from a name, and so there are libraries out there that are using it for other purposes. I think probably you'd most commonly encounter it in the context of kind of optics or lenses libraries, but I think they're sometimes interpreted as, if you like, sort of constructors where you don't necessarily have to define all the constructors up front, but it can somehow make use of more type information.
Okay, then let's see. I mean, this has already been discussed on the channel, but I guess nevertheless, perhaps good to reproduce. Does optics have something like lenses make classy to automatically make a class like hasName that lets you use a name lens for various records with such a field?
We do have make classy. I perhaps should have mentioned this already, that indeed so lens has this approach to this kind of problem where you have template Haskell generate a type class specific to the type of the field name, and then generate multiple instances of that class for the different types that have name fields. The downside of that approach is that you have to sort of pick somewhere to actually define that class in those instances. And so if you kind of have somewhere at the top where you can top of your dependency tree where you can just define this, define all these classes that you need for the different fields, then that's fine. But it sort of assumes a closed world, and that you need to know what all the fields are going to be. And so if you want something that you can just kind of have multiple packages that don't depend on each other, that might talk about fields with different names, then that approach kind of can be less pleasant to work with. But it is supported by optics if you choose to use it.
Yeah, another question that has actually been retracted in the meantime, but I'm nevertheless going to ask it. Is there a version of the overloaded label stuff that uses template Haskell to generate instances rather than generic?
Yes. So you notice that I defined this is label class instance using a label optic class. And I haven't actually shown the definition here on the slide, but so label optic has got a catch-all class instance that uses generics, but you can also override that by defining your own instances. So if you give an explicit instance for label object, and in particular, if you give such an instance using template Haskell, then you can use that instead of the generics mechanism, and that means that you can insert effectively a manually constructed or a template Haskell constructed object that doesn't go through generics. And so if that's a potential performance problem, then you can insert that.
Yep. There is one more, I think, rather interesting question from Michael. Is there a way to make overloaded labels properly scope identifiers? Current syntax seems to use a symbol without any regards to module imports, exports, etc. I can imagine we may have two applications of, for example, the word pet in two different modules. In one, it means pet animal. In another, it is a verb indicating an action. What then?
So there are multiple sort of facets to this, I think. So one aspect is just the representation hiding aspect, that you should be able to define a module and have a data type that has some fields internally, but if you don't export those in the public interface to the module, you shouldn't be able to access them outside of it. And that is in a sort of intermediate state at the moment, because indeed with generics we don't really have a way to do representation hiding. The plan is that the overloaded record dot functionality that is needed to support the extensions we need to overloaded record dot in order to be able to do updates, basically should also give us the ability to stop using generics for label object and instead use hasField. So that's this built-in class that gets solved automatically by GHC. And crucially, hasField does take account of whether fields are in scope. And so that does get back representation hiding. I think at the moment we use hasField for selection but not update. So I think you'll sort of get representation hiding, but at the moment, but that should improve in the future when we're able to reuse the hasField mechanism for label object. I mean, the other part is about, well, actually, I might have two different meanings of the same symbol in different contexts, and so really I might want to say that actually I am going to scope these labels rather than just having them as sort of free floating symbols. And my answer to that would be that the idea of these classes is not to expose them in your public API. It's as a mechanism for the type inference algorithm to figure out which fields you're talking about and which kinds of objects and so on. So I would discourage you from having a function in a public API that actually was polymorphic in a label object or in his label or a hasField constraint. Right, so they should be used to at a call site to say, well, what do I mean by pet at this call site, rather than being part of the public API. And I think then it becomes much less of an issue to say that, well, the same string might mean different things in different contexts, because it's much closer to what we do just with kind of accessing names already. That I mean, yes, depending on what's in scope, you'll get different functions when you write the same name, because that's just what it means to be in scope. I mean, does that make sense?
it's difficult to judge for me, but I think
when you're relaying the question. But
I don't see people complaining loudly on the channel right now, so perhaps let's leave it at that for now. And
okay, so I mean possibly that sort of lets us transition a little bit to talking a little bit more generally about lessons about library design before we finish. So we've seen a little bit of kind of some key optics and how those are captured in the optics library and how we can use that with records. I mean, I think there's only so much one can say in a talk like this, and I strongly encourage you to take a look at the exercises and play around with the library yourself to actually get familiar with some of this. But I wanted just to reflect a little bit before we finish about library design and interfaces, because that last point about not being polymorphic in constraints that talk about field names is, I think, indicative of a more general issue. But first, I just want to reflect a little bit about this pattern about how we've been defining interfaces and optics. And if you want to go and explore it further, kind of that you'll see this pattern again and again in the modules that define the different optic kinds. That we have type formation rules, introduction rules that say how you build the thing, elimination rules that say how you use it, combinators that say how you put more than one of them together, and laws that say how you can reason about the type, what it means. And I think something we don't always think about as Haskell programmers is are we capturing the abstractions that our libraries are working with, and are we sort of crystallizing them in this way? Are we thinking in terms of what is the public API that I should be supporting, and are we using implementation hiding to make sure that we're not exposing too many details of the representation independent of the interface? I think a concrete example of where this exposes a difference between optics and lens is the context in which you can use view. So we very much take the position that types express the meaning, not just the structure of the data that we're working with, and therefore it's reasonable to impose constraints beyond just what the structure gives you. So in optics, view says that you need to supply a getter in order for the function to work, whereas in lens it's defined in such a way that that actually, while you can use it for getters, you can also use it for an arbitrary fold. And how does that work? Well, because view is supposed to return a single result, and a fold might have multiple results. Well, we're just going to assume that the type being returned has a monoid constraint. So that if you use view with a fold, we'll just get an extra monoid constraint popping up in the return type. And in fact, you can see that the inferred type here is actually more general still, because there's this monad reader constraint coming in instead of just a function. And I think that sort of illustrates the philosophical difference, that we want to be able to say actually that there is a well-defined interface to what it means to be a getter, and folds just don't satisfy that interface, so we don't expect this to type check. Instead, you should be using an explicit operator that works on folds, and indeed there is one that says, well, just give me the result of combining all these monoidally, but that becomes an explicit choice from the programmer. I think more generally, there's a a story here about implementation hiding too, as I've mentioned a few times, that we want to be using the module system to hide the implementation details that we don't want users of our libraries to have to look at. And I think, I mean, one interesting possibility that Object offers here is that rather than exporting a record with its fields as part of the public API of your module, by using smart constructors and lenses, you can give more flexibility later to change the representation. Because if you just expose as part of the API that there's a lens to modify a certain field, then if you later change where exactly that data is stored within the internal representation of the data type, then that doesn't change the public API. Whether that's a good idea or not yet, I think the difficulty is, of course, that you then commit to a particular representation of lenses in a particular library potentially. But it's, I think, something to consider as a possibility. Another general lesson I'd like to draw is that actually, why do we use type classes in Haskell? I think there are sort of two reasonable reasons and one less reasonable reason. So if you need overloading when you want one identifier to potentially have different meanings depending on its type, then fair enough. You don't necessarily want to have to write different functions for converting every different type you work with to JSON, for example. Or if you want to take advantage of the global coherence properties that say that, for example, there's one canonical way of ordering values of a particular type, and therefore you can store them in a map and know that you'll get the same ordering in multiple places. But we don't necessarily need to use a class just in order to introduce an interface. That we've been talking all along here about. This is sort of how we define the interface without necessarily having a class whose methods are the operations that we support. I think there is sometimes this assumption that if you want to introduce an interface in Haskell, then you use a type class. And actually, that doesn't necessarily help matters and can indeed make things more complicated. We can tend to reach for polymorphism very quickly and assume that by making something more polymorphic, we're making it better. But actually, once you make a definition polymorphic, we have to ask, well, is the compiler going to be able to infer the types that users mean, and will people reading the code be able to infer the types at which identifiers are being used? So we've carefully designed optics in such a way that we get good results from type inference. And we do that by having these introduction forms return a concrete optic kind, so that if you call the lens function, then you get something of type lens SDAB. Whereas if you use an elimination form, then that is polymorphic in the optic kind that you're eliminating to allow for the subtyping we talked about earlier. But crucially, we only want one of those two, because if we had both of them polymorphic, then we'd have no hope of type inference giving good results. So I think the lesson here is to think about how is type inference going to work with the module API I'm designing, and is it going to give good results in the situations in which it's users going to try it out. If we have too much polymorphism, then there's a risk of ambiguity, and can be confusing for users, and it can lead to things type checking that we don't think should type check, like in the view with the fold example. I'm going to skip over issues about more complaining in this direction, because I want to get to finish with a bit of time for questions and discussion at the end. But I do want to sort of highlight one anti-pattern that I think does tend to arise, and certainly I've seen in some Haskell code bases. And I'm switching a bit to talking about MTL rather than optics, but I think this can arise in lots of contexts, not just in MTL and effect systems. And it's the pattern of having constraints bubble up, propagate upwards from kind of the definitions at the leaves, if you like, to the main function. So here's a sort of simple example of what that looks like. Well, I've got some do stuff function which I've made nice and polymorphic, and I've said, well, as long as M supports I/O and M has an integer available to read, then I can call this method, and that's nice and class polymorphic, and I can use it in any context that satisfies these constraints. Okay, and so I'll have another operation somewhere else in my app that needs to call do stuff and does some more stuff, and so that needs all the constraints that do stuff needed, and then it also needs some other constraint, main-add writer, to be able to do whatever it needs to do. And then ultimately, what do I end up doing? Well, I instantiate this with a particular concrete choice of M. I've made this polymorphic in main-add I/O here. I could also specialize to I/O at this point. And so what's going on here is we're sort of starting with all these little bits of code and saying, well, which constraints do they require, and making them polymorphic over those constraints. And that sort of feels like it's going to be nice and general and will allow me to use things like do stuff in any context in which I can satisfy the constraints. But in practice, what tends to end up happening is it just becomes more and more complicated to satisfy all these constraints. And in practice, I probably only ever end up instantiating them at one particular type. But maybe I only do that at the point at which I call the main function. And so, I mean, as I say, I've picked on MTL here, but I don't think this is particularly specific to MTL. I think it's a common pattern where we start at the bottom and bubble the constraints upwards. As I mentioned, that could happen with overloaded labels as well. If you sort of start by saying, well, this will work for anything which has an overloaded label satisfying this. I mean, this is label constraint, or writing a function that says, well, I'll work for any record type that has a field foo using the has field class constraint. And what should we be doing instead? Well, I think a more top-down approach. We should be saying, well, what are the interfaces between the components of the software I'm developing? What are the types of the different components? And so rather than sort of bubbling these constraints up from the leaves, just start from the top and say, well, this is how I'm structuring the program, and these are the requirements that this component must fulfill, and push down those requirements, make the type as specific as possible, ultimately then hiding the implementation details between the appropriate layers. And then I think you'll get something that is clearer and easier to work with, and optimizes better as well, because one big cost of this approach of having all these constraints bubble up is precisely that if once things start getting too big, GHD isn't going to necessarily specialize away all the overhead of passing around all these class dictionaries. And so if we make everything rather more concrete and say, well, rather than being polymorphic in all these class constraints, I'm going to write down a new type wrapper around the main-add that I want to use. hide that implementation, and then use that. Well, because it's defined up front, there's no dictionary parsing, there's much less to go wrong when it comes to specialization. And that's the point at which I wanted to wrap up with the bulk of the talk. We have got a little bit of time for questions and comments and discussion. I'm very happy to continue discussions on the optics channel on Discord. In particular, if you want to have a look at some of the exercises and resources in the GitHub repo over the course of the weekend, then please do, and ask questions on this channel, or and then have a play with optics, try it out. I mean, we've only really, I think, scratched the surface here, but I'm hoping that by kind of illuminating some of the design principles, that might give you an entry point into exploring the library. And I will ask if there are more questions or comments.
I must admit I'm probably partially responsible by cluttering up the channel with an ongoing discussion about the efficiency of generics versus template Haskell, which has been ongoing, but it hasn't really been resulting in concrete questions for you. I'm sorry for basically derailing the on-channel discussion. Please, if there are any more questions for Adam, you can ask them now. I think there is a question: is there any concrete example of this proposed by you top-down design principle, as opposed to this bottom-up anti-pattern that you have been describing?
Yeah, I should have put together a slide with with the top-down approach as well as the bottom-up one. I mean, of course, it's always hard to illustrate something that I think sort of goes through the app as a whole. I mean, what I think is going wrong in something like this is really that we're sort of using polymorphic types because those are the types that the compiler inferred for us when we wrote down the definitions, essentially. And so what would it look like to do something differently? Well, that would mean starting with writing down what is the interface that do stuff provides, what are the concrete types that are involved, and then so in this case, I mean, maybe so depending on the context, we might want to introduce a monad that has access to this integer, whatever it means, as well as being able to do I/O, and we might define a new type wrapper to sort of capture that stack and use MTL to implement the monad instance and so on. I think a pattern that's worth looking at, which I never got around to make a slide about and should have done, is the sort of handle or service pattern, as I think it's sometimes known. Jasper had a good blog post about this some time ago, I think it was, which talks about how you can write down a sort of have a data type representing the capability to do some operation and pass that around just as a normal value, and then have a nicely defined interface that works on that value. I'm sorry I didn't condense a nice example of that.
Okay. Let me see. There are a couple more questions now. Perhaps staying with this, like for the time being, would class constraint discovery by using some form of like partial type signature, like with an underscore for the constraint, also be an anti-pattern in your opinion?
I think I mean, I wouldn't want to say that you should never do these things, but I think if you can't write down what the constraints are, then that suggests that they're probably getting a little bit too complex, and it's worth thinking about how to restructure things in such a way that they don't. I mean, I work with libraries where that was the only sort of feasible way to actually write down what the type of a function was, because it was just too complex to work out. And so yes, I mean that obviously that can be useful as a kind of exploration technique, but I think if you can't give your operation a clear type signature that doesn't have far too many constraints, then something's going wrong.
Mm-hmm. Okay, and then there is a question which is difficult because it involves code. Is there a way to define constrained optics like? And then, essentially traversal C type synonym, which has an extra constraint parameter, and then essentially a profunctor optics kind of encoding has an additional use of this C with the optics library.
I don't quite know what's going on here. So perhaps we should discuss this on the channel a little bit more.
Yeah,
I mean,
seems a little bit complicated.
So it is generally the case. I mean, that there is a sort of general pattern, particularly with profunctor optics, but it isn't quite this pattern. But I wonder if that's what's meant. So sort of under the hood, there is actually a sort of notion of constrained optic for a constraint that's selected for. So depending on the optic kind, we select a different constraint in each case. So I think probably under the hood, optics works in a way similar to what's being described here, but it doesn't quite match the type that's there. And I think probably we can't go into the full details of the difference in the time we have left.
Yeah, okay, so let's perhaps discuss this later on the channel. There is another question. Do you miss anything in particular from lens when you're working with optics?
I mean, in a sense, what we've tried to do with optics is sort of port over the bits of the lens API that we, being the optics authors, sort of collectively think are most useful and are the bits that we want to use. So in that sense, I mean, certainly there are times when, I mean, there are lots of functions that lens provides that optics doesn't, and in many cases that's just because we haven't got around to implementing everything. And I mean, I should particularly give credit to Andrzej Rybczak here, who's done a huge amount of work on sort of turning optics from a vague idea into a library that actually encompasses a lot of functionality. And so I've sort of used optics and ported code to it. That because it fits my prejudices about which parts of lens are the most useful, it supports what I need. I mean, I'm sure that other people will find different parts of the lens API useful to them, and not all of that will be present in optics. And I think we are.
Do you think everything is in principle portable, or are there things in lens that like cannot easily be ported if one just invests the time?
I think as far as I've seen, every kind of, if you like, public interface that you might want, we can port. But I'm not aware of anything that's fundamentally impossible. I mean, you do sometimes get kind of, if you like, more noise. You need more. I mean, where lens will just let you use traverse from base directly as a traversal, in optics you need to have a different name for it because we're making a type distinction that isn't present otherwise. But I think apart from kind of needing to introduce those type distinctions, and sometimes maybe having more kind of type classes behind the scenes to make things work, I don't I don't believe it's something that we fundamentally can't do out there. Or if there is, I haven't seen it yet.
Okay, then there is a question by David Lindbom. If I want to supply lenses for my library, can I make it usable by both optics and lens, as they use different representations?
That's a good question, and indeed one of the advantages of lens is, as a library author, you don't have to depend upon it at all. You can simply write your lenses using base. I mean, you'd have to define some combinators yourself, and there are other lens libraries out there, notably MicroLens, that kind of give you a few of the most crucial combinators without being such a heavy dependency. So with optics, you necessarily have to depend on optics core in order to be able to give an optic, because you need to get access to this new type. So I mean, probably the lightest weight option is to just define a Van Leeuwenhoek lens without kind of pulling in any external dependency or using something very very light. Yeah, I mean, otherwise, kind of you can depend on optics core and give an optics friendly version of the API. But I think it's not unreasonable to sort of define the Van Leeuwenhoek lens is the thing you expose with your basic package, and then potentially have an optics variant of it that just adds the optics USAT wrapper for people who are using this library.
Okay, I think there are, I mean, probably some things that I have overlooked, but I think we have like handled most of the questions, and I think it's probably a good point to stop, because we probably all want to attend the panel discussion with Simon Peyton Jones, which is starting in a few minutes. So I think I'll say thank you, Adam, for the nice workshop. I hope everybody enjoyed it. And yeah, tomorrow we'll be back with this tutorial on memory usage and debugging with GHC and Haskell by Ben Gamari and Matt Pickering. So hope to see you all again. And the channel, of course, will stay open for further discussion, and we'll be around all weekend. Yeah, thanks.